I think I was wrong about videos looping around automatically, but nevertheless I'm going to make title pages so we can see easily by looking at the video what it's about. So I want to talk about triangular matrices. So recall that A is upper triangular if all of the non-zero entries occur on and above the diagonal. So this matrix is upper triangular because everything below the diagonal is 0. Equivalently, everything that's not 0 is on the diagonal or above it. Now we're allowed to have zeros above the diagonal, but we're not allowed to have non-zeros below the diagonal. Sometimes I'll just write a triangle for upper triangular. Now let's think about the indices I and j. So in the 1, 3 position, we've got non-zero. In the 1, 2 position, we have a 0. In the 1, 1 position, we have a 1. In the 2, 1 position, we have a 0. In the 3, 1 position, we have a 0. So if the first index is greater than the second index, we must have 0. If the second index is greater, we might have 0. So when I is greater than j, we certainly have an entry that is 0. Now I claim that if you multiply two upper triangular matrices together, you get another upper triangular matrix. Let me show you why. So let's let C be the product AB. And let's say A and B are n by n. Just so we have a name for the dimension. So that means that the ij entry of capital C is the sum as k goes from 1 to n, because the matrices are n by n, a, I, k, b, k, j. Now since a and b are upper triangular, we have aik equals 0 when I is greater than k, and bkj equals 0 when k is greater than j. So that means that we can rewrite Cij. We don't need to sum from 1 to n, we can just sum from I to n. Because if k is less than I, this is going to be 0. So we can sum as k goes from I to n, a, I, k, b, k, j. And what does it say about Cij? What happens if I is bigger than j? Is it certainly going to be 0? I think I'd better erase the top part. Suppose I is greater than j. Now k is varying from I to n, so that means that all these indices k are going to be greater than j. So all numbers k from I to n satisfy k is greater than j. But if k is greater than j, then bjk is 0. So that means that all the factors bkj in the terms of the sum are going to be 0, and then the terms of the sum are going to be 0. So that means the sum is 0. And Cij equals 0. So Cij being 0 when I is greater than j means that C is upper triangular. Sometimes at the end of a proof we write QED, which is Latin for something like "this has been demonstrated." In Italian it's "questo è dimostrato." But I don't speak Latin, so I can't say the Latin for you. So if A, the matrices A and B are n by n upper triangular, then their product is also. I meant to call that claim 1, because now I have another claim, which I'm going to call claim 2. Let's let A and B be n by n lower triangular matrices. Then so is their product. Now I guess I could do the whole proof over again that I did for upper triangular matrices, but it's so similar that I can capitalize on what I've done so far and show that that implies that this claim is true also. So by the claim that I meant to name claim 1, B transpose A transpose is upper triangular. Well, that's because B is lower triangular, A is lower triangular. And when you transpose a matrix that's lower triangular, you're putting all the non-zeros on the other side of the diagonal and you get an upper triangular matrix. So these are two upper triangular matrices and their product has to be upper triangular by claim 1. Thus, if we take the transpose of B transpose A transpose, now remember when we take the transpose of a product, it's the product of the transposes but in the wrong order. So it's A, this is overkill but I'll write it out. A transpose transpose, B transpose transpose, which is AB. Now if what was inside the parentheses is upper triangular, and we transpose it, we get something that's lower triangular. And that's all there is to show. So the product of two lower triangular matrices is lower triangular. Now we call a matrix upper or lower unitriangular if it's upper or lower triangular. And has only ones on the diagonal. So for example, here's a matrix which is upper unitriangular, because it's upper triangular and all the entries on the diagonal are 1. Now I claim that if you multiply two upper unitriangular matrices, you get another upper unitriangular matrix. So if A and B are upper unitriangular, then so is AB. So let's C be A, B. So by claim 1, C has to be upper triangular. Furthermore, for all I, we have CII equals AIK BKI, summed as K goes from 1 to N. Now if I is greater than K, then AIK equals 0. And if K is greater than I, then BKI equals 0. So that means that almost all of these terms are going to end up being 0. The only way that we could get one that's not 0 the only term that is not 0 is A, I, B, I. Now since A is upper unitriangular and B is upper unitriangular, that means the diagonal entries AII and BII are both 1. So that means the diagonal entries of C are all 1. Questo è dimostrato. Now, of course, the next thing I claim is if we have two lower unitriangular matrices, then their product is also. So let's let A and B be n by n lower unitriangular matrices. And so is AB. So by claim 3, B transpose A transpose is upper unitriangular. Because if A is lower unitriangular, A transpose is upper unitriangular, and same for B. And then a product of two upper unitriangular matrices is upper unitriangular by claim 3. And then if we take the transpose of this, again, when we take a transpose of a product, we have to reverse the order and take the transposes in that order. So if this is upper unitriangular, then its transpose is lower unitriangular. Questo è dimostrato. And that's enough for now.